Hello community, so great that you are back. You know what? Whatever I thought to know exactly about reinforcement learning might turn out to be not correct. Because I thought, reinforcement learning here is regarded as, it is the promising approach to enable LLMs to continuously self-improve, especially our vision language system, our robotic system. We want that the robots walk around and they self-improve continuously. And they acquire new novel reasoning capabilities. And everybody would tell you, yeah, this is of course reinforcement learning. It has to be reinforcement learning. Now, guess what? I want to provide additional value to you with my YouTube channel. And therefore, today, April 21st, 2025, I'm going to tell you, we will challenge here this central assumption in the current LLM post-training pipelines. And this will change the future. So let's have a look. You noticed on my last video, which was an absolutely beautiful video, I left out here reinforcement learning. And you might guess, hey, is there a particular reason for this? Yes. And it is a beautiful coincidence that today a new paper by Tsinghua University was published that is spot on. Sometimes you get lucky. So let's talk about reinforcement learning with verifiable rewards. Reward systems, we have binary reward systems here and one, a complex reward system and stepwise reward systems. Let's go with the simplest one. Does it really induce reasoning capabilities that go beyond the pre-trained language model? Is this really possible? Because let me ask you one question. Where the hell is this reasoning capability coming from if we have an AI as a pattern matching machine? Now, it turned out that this beautiful reinforcement learning with verifiable rewards optimizes the LLM by using here binary rewards, bypassing here the human annotation. This is done synthetically and this is great. And everybody knows, hey, yeah, OpenAI, and especially DeepSeek R1, this fueled the hypothesis that reinforcement learning enables LLMs to autonomously acquire novel reasoning patterns and surpass their initial pre-trained capacity. Self-learning robots, self-learning humanoids. Isn't this beautiful? And you know what? I will induce an emotion in you because we're going to ask now a very simple question as a scientist. Is this true? Let's open up the video and have a little bit fun today, yeah? So, reinforcement learning, the path to smarter AI models. And maybe you can read this subheadline and it says, a surprising limit emerges in our research. So, we have a core hypothesis, now. This reinforcement learning expands here the solvable problem space. Now, if we think about higher dimensional, let's think about a vector space, a tensor space, whatever you care, you say, yeah, this is it. Now, this will go beyond the reasoning capability boundary that we have with our pre-trained model. Now, this is the sole reason why we do reinforcement learning. Yeah? And there's a little voice in the back of your mind and says, that reinforcement learning, by human feedback, it was to align the model more in the behavior of the model. It was originally not as a PPO, as a policy optimization designed to add new knowledge. And this little voice in the back of your head tells you, or maybe there's an alternative hypothesis. Could this be true? That this reinforcement learning primarily optimizes here the sampling efficiency within the reasoning pattern already implicitly encoded in the pre-trained base model. So this means it is not generating new research capability or reasoning capabilities for research, but it is just better in sampling, picking more efficient reasoning patterns that already exist in the pre-training. Could this be the cause? So let's have a look at this. And there's one beautiful example. I read again here the DeepSeek, the open source R1 paper here and the R1 Math paper. And you clearly see this reinforcement learning tuned models exhibit a higher PAS-1 score across mathematical, coding, visual reasoning benchmark. So this clearly showed us, absolutely, that the reinforcement learning effectiveness in increasing the likelihood of sampling here correct reasoning path in the initial attempts. So yes, it is great reinforcement learning, There's only one absolute insignificant, you call it a minor detail, yeah? K equals 1. What happens if you leave K not at 1? So you say, but hey, the first experiment tells us, no, if I only have one run, then reinforcement learning is really great. And you are absolutely right in your argumentation. And this is exactly what I thought. If you only have one run, then yeah, this holds. But what if you have 2 identical runs? So let's explain this posit K, a metric simple evaluating the probability that a LLM generates at least one correct solution for a given problem, for a given query that we have as humans within K, 1, 2, 3, 4, 5, independent attempts or independent samples, whatever you prefer. So this is our central metric used to probe the reasoning capabilities now for years. And if we have a real low K, K equal 1, it measures the sampling efficiency, how likely the model is to succeed quickly. But you have other Ks, 256 up to 1K. And this now is used to estimate the reasoning capability boundary, the scope of problems the model can solve eventually. Give them enough time, give them enough compute, give them enough energy. So now the problem is, wait a minute. If we up until now looked only at the very first attempt, what if we let the model run 2 times, 3 times, 4 times with the identical query and we have then simply a majority vote on it? Because guess what? This is exactly what we do. So this now allows here the decoupling of the initial performance efficiency from what is the ultimate potential problem-solving reach of the model, of the pre-trained model. And do we need reinforcement learning at all? And if so, for what particular task? So, let's have fun. Let's have here a spark of genius. No, and the spark of genius comes from our Chinese friends here at Tsinghua University. I have a beautiful new paper published today, and they go now to a moderate K. Tens, maybe up to a slight 100, not only 1. And this increasing K parameter now reveals a diminishing advantage of our reinforcement learning models. And you would say, how is this possible? Base models, the pre-trained LLMs and vision language model, our robotic system, despite a lower initial efficiency, consistently improve here their posit K scores, eventually matching the performance of their reinforcement learning counterparts as K reaches now tens or maybe a slight 100. So this suggests now that we have absolutely a comparable underlying theoretical and real effective problem-solving potential of the base LLM if I compare this to the reinforcement learned aligned large language model. The only thing is, moderate K. K now is 15, 20, 25. And then the third step here, you see in beautiful pink that it really pops out here is, what if we go with K higher? 100, 200. Then the base model, our pre-trained LLM, surpass the reinforced learning models. The base model achieve now a higher success rate than reinforcement learning based models. Yeah, you have here at K128, you see an effect already of close to 10% improvement of the base model to our highly aligned and trained reinforcement model. Imagine the time that we wasted. Imagine the energy that we wasted. But there's another point to this. This signifies a larger intrinsic reasoning capability space within the base model. Now, this sentence knocks you into the stomach. Think about what this means. This means that the base model, if you imagine here an abstract solution space, and the base model now shines here. Let's imagine it's a dark room and you have a flashlight in your hand. You open the door, it's dark. And you switch on the flashlight, and now you hold the flashlight here at position 1, position 2, up, down, left, right, to the floor, to the whatever in the room. And then you have 128 flashes from your flashlight. So you explore the complete reasoning space. You explore the complete dark room in front of you. And now, interestingly, the base model has a higher capability discovering new, better solution than the reinforcement learning model. And this really blew my mind. I said, unbelievable. And you know what? This is exactly what we do with multiple parallel probing here if we run this in parallel and test time scaling for our reasoning models, no? I don't care if I have to wait already 2 minutes or 5 minutes or 6 minutes. Okay, I run the same query 128 times, but you know what? Somewhere in this 128 runs, there's a solution that is so much better than the reinforcement learned model. I want this performance right now. So, let me show you this, and this is here from the publication of our friends here in Tsinghua University. Thank you for publishing this. I'm loving this study. So we have here a problem, and we have a base model, no? And here we have this beautiful new with a lot of energy and a lot of data and a lot of alignment and syntactic data and whatever reinforcement learning model. And you see both are now searching for solutions. This is not a flashlight shining here in this dark room, you know? Flash here, and then from here we go deeper in the tree. And you know what's happening? Beautiful. They both find the solution. Here's a +1 and here's a +1 indicating this is the valid solution, and 0 would be no. So base model and here this model, great. Now the point is, if you just go with k equal 1, the reinforcement learning model achieves this faster. But there's a major disadvantage with this. Because if you go to problem B, being faster reduced now your scope of the problem space. Because shining only here with the flashlight in this direction of the reinforcement learning model that is fast, it ignores the other half of the dark room. And you know what? For problem B, the solution is on the other side of the room. Please, this is an analogon. You understand what I want to tell you. Therefore, the base model finds a solution now, a correct solution, a valid solution, that the reinforcement learning is not able to find at all. So we do have kind of advantage with the reinforcement learning regarding the speed, but we have a major disadvantage if you go for high quality solution. Now you might say, yeah, but this is not valued for every domain. No, maybe this is some test domain specificity. And so let's have a domain analysis 1, mathematical reasoning. Let's go with AIM24. No? So across all the data set, and they tested this here for whatever data set, and they used multiple LLM families. They used the Q1 families, the 7B, the 14B, the 32B. They used the Llama. Yeah. 4 you can forget, so they rightfully stayed with Llama 3.1, and the pattern holds. So for mathematical reasoning, the reinforcement learning yields substantial pass-1 gains and speed gains, but fails to extend and often contracts even to higher k pass at k boundaries relative to the base pre-trained model. So this new thing that breaks here whatever I believed yesterday is valid for mathematical reasoning. Let's check another domain, code generation and visual reasoning for our robotic system. No? Our little robotic humanoid, they walk around and they learn like little babies, like little human babies. No? And they have to have a self-learning mechanism, and we all know this self-learning mechanism is reinforcement learning. Now, starting today, we know this is not correct. They found here, even with code generation, visual reasoning here, that this observed limitation is valid and therefore not domain specific. And they did this here with code R1, different benchmark, and easy R1, and mathematical vista, and MadVision, and whatever. Reinforcement learning here optimizes the initial performance, but the base model retains a broader, ultimate problem-solving scope revealed by a large K evaluation. So it is better to let the base model run multiple times. You will get better solution even with coding and individual reasoning. So therefore we come now to an intermediate conclusion. This collective evidence indicates now that this reinforcement learning primarily functions to increase the sampling probability of existing valid reasoning path within the pre-training base model distribution. The probability distribution we have induced by the pre-training alone, rather than inducing here what we believed fundamentally novel reasoning patterns, or expanding here the theoretical solvable problem set. They found this is not happening. This has massive implications now after training of the next generation AI. And if you think they did this only here for one reinforcement learning algorithms like GRPO from R1, no, they went with PPO, they went here with different DPO. I have a specific video on this. You can check out here the different RL algorithms. They went with different models, with different frameworks, with different benchmarks, and they always found the same result. Yeah, they also went with a different metric, evaluation metric, perplexity. This is if you're not familiar with this. And the facts are absolutely amazing. Eh? And here, this study here, April 21st, 2025, does reinforcement learning really incentivize reasoning capacity in LLMs beyond the base model, the pre-trained model? And we have this here by Leap Lab from Tsinghua University and Shanghai Jiaotong University. Thank you. What a beautiful study. And yeah, of course, they have a GitHub page. I'll show you in a minute. And they have now this analysis. They say the solution that the reinforcement learning aligned LLM finds are largely just a subset of the solution that are inherent already in the pre-trained LLM. There is no new reasoning pattern. There's no advanced reasoning happening above that of the pre-trained model. And they do this here for GRPO, PPO, Remax, whatever, Reinforce++, for the different algorithms. Really nice. Have a look at the paper. They have so much more data and ablation study and everything I can't show you because I just want to focus here on the main event. So they say direct comparison of the problem indicates solved by is here that the set of problems solved post reinforcement learning trained is predominantly an approximate subset of those solvable already by the base model. The conclusion is that reinforcement learning rarely unlocks here problems entirely inaccessible to the base model, to the pre-trained model. So reinforcement learning brings no new reasoning traces. And you can have a perplexity distribution analysis, and this quantifies here the sequence likelihood, and you can do this, but it brings you to the same result. Research results implies reinforcement learning favored path were already highly likely in our sequences under the pre-trained base model. So our probability distribution of the pre-trained model, they generate the reasoning path and the reasoning traces. And RL contributes nothing to new reasoning traces. And honestly, this is a shocking result for reinforcement learning. This breaks with my knowledge and my expectation I had for reinforcement learning. But you remember, if you think back here at a PPO, the policy optimization here, or DPO or TPO then, and all the GRPO and whatever algorithm that we later developed, no? It all started with aligning the behavior of the language model. And never at the beginning it was to train the LLM on new knowledge. And now I come back to the topic in my last video. Because in my last video I showed you exactly, in the last two videos, that the prior imprint on the pre-trained LLM is massive. And now we see this here confirmed by the study published today by Tsinghua University. Yeah, If you want to see here the prior, this is the video for you here. MCP and A2A fail, but not for the reasons you think. Here I have a deeper, more detailed look at what's happening here behind the code. We talk about policy gradient variations and so on. Trying to interpret here and make understandable what's happening here. So, given now the strong pre-trained LLM prior and the sparse rewards in the vast action space, this optimization predominantly just reinforces existing high reward paths generated by the pre-trained model, reducing now, and this is maybe the only positive effect, the output entropy, and consequently now we come to the negative effect, limiting exploration and the effective reasoning boundary. Because reinforcement learning is so fast, it focuses on one solution, Think about if you have a lot of solution and solution space, the one solution that shouts the loudest and says, I'm here, look at me, I'm the best solution. Reinforcement learning kind of says, okay, you are the one, come on, you are the one. And it ignores all the other solutions that may be not as loud shouting in this room, but are much more efficient in solving our queries, our problems. So it is limiting here the exploration space to find out, hey, there's the perfect solution to our problem hiding in the dark corner here of this vector space. Yeah, I'm a little bit early because you see they're just starting here to fill up here the GitHub repo just 5 hours ago. They started here to put in the data. So whenever you see this video, I hope there's much more data available. But this is so nice. I love this study. Have a look at this yourself. Read it yourself. You will enjoy this study. Let's come back to my last 2 videos because I want to provide value to you as my viewer. What is now the effect from this video? Knowledge. If we want to have LLMs, vision language model, robotic system that learn autonomously, and we now found out that reinforcement learning is not the way to do it. What is it? Surprise, surprise. Distillation. The video, 2 videos back that I have is exactly the solution. And we looked at distillation in multiple of my videos, and they run the test here, this particular test here at AIM24, and they have here, now look at this. Here in green, you have the base model performance, and the number of K, the number of samples they run this here. And here you have the path at K, 20%, 40%, 60%, 80%, or close to 90%, I would say, is the upper limit here. Base model in green, this is the base model. This is the pre-trained model. Then the instruction-based model, you see their performance is not as good because instruction-based means for a specific task. Now, this is maybe a general test, and yes, it is a general test, so this task is not as optimal. But if you do now here in, let's say this is orange, the reinforcement learning that we just talked about, you get a certain improvement. Yes, you found here the one fast solution. So from the complete solution space that has, let's say, I just imagine 15 possible solutions to our query, you find one solution fast and you have it here in the orange. So you are better than the base model. But imagine you do the distillation. Look at this curve. The base model starts here at, 17, 18%. The reinforcement starts here at 30%. And the distillation starts at 50%. And then look at the performance in black. It outperforms everything else that we have. Isn't this beautiful? And in my last 2 videos, I also showed you how we can optimize the distillation. Hey, all the videos belong to a little mini series. Maybe I have to have a certain playlist. I'd have to generate a playlist for this to make this more clear if you're new to my channel. So let's formulate this here. For knowledge injection into our robotic system, our language system, our vision system, distillation demonstrates here a real boundary expansion. So in stark contrast, knowledge distillation, fine-tuning and outputs from a superior teacher model, let's say the full-fledged R1 671B model, demonstrably expands here the parset K reasoning boundary significantly beyond the base model of 32B or whatever you have. So this indicates now a successful incorporation of new reasoning patterns that were really absent in the base prior. This is the methodology that works. This is the methodology you should use, not reinforcement learning. Great. This was the value of this video. Have a look at reinforcement learning. There is an added benefit because now we understand what it is really doing in the internal networks here. You know what? Now we can use it here as an inference time optimizer. So up until now, we were talking here about the training time scaling optimization. And we find out, you know what? We can do this, as I already showed you here, where we have inference scaling, the reasoning models. I wait 2 minutes, I wait 6 minutes. Okay, run the same question 50, 100 to 128 times. Take the best solution and present me only the best solution. So for the inference time of our reasoning model, it turns out this is now a beautiful optimizer. But of course, we have to have the right model for then those inference time scaling. So therefore, this reinforcement learning should perhaps be viewed less as a mechanism for learning new reasoning skills and more as a real powerful technique for optimizing here the retrieval and the execution of reasoning capabilities already embedded in the training time scaling within the pre-trained base model. And these fundamental limits appear set by the pre-training. So the pre-training determines your reasoning capabilities, and the continuous pre-training from my last video I showed you also improves this if you do it in the right way. See my last video. But reinforcement learning fails. Reinforcement learning, now we understand today, shines somewhere else in the test time compute scaling. So therefore, if you want a future challenge, transitioning now from the optimizing known reasoning in the pre-trained LLM to discover the unknown reasoning path. And today we know, we can prove, we have the data, it is not reinforcement learning. And this is sad, but it is also fascinating because it opens complete new avenues that we have to discover. So let's end this video here with the official wording here by our colleagues here from the study here from Tsinghua University. And they tell us here 3 main points. Reinforcement learning with your reward system does not elicit novel reasoning abilities beyond the base model, beyond the pre-trained LLM. Reinforcement learning improves here only the sampling frequency if we go here with k equal 1. But at the same time, reinforcement learning, if we go with a low k, narrows here the reasoning boundaries, reduces here the reasoning complexity this reinforced learned model can apply. It is handicapped because it just can look at fast and quick and dirty solution. And it has not the complete reasoning space like the pre-trained model has. Remember my example with the flashlight? With the base model, you have to flash here, flash over there, flash here, flash there. You have to go maybe 128 times to scan the complete dark room. But then you find it. Reinforcement learning would not even find it, the best solution to your query. So there you have it, today's video. A pure coincidence that our friends here in Tsinghua University published here this beautiful study, but you see, it is the same question in the AI research community. We are all asking here the same question. Is this really working? And just because we have indication, and maybe it will work, that we will now focus every resources here on this just idea, and we don't try it out, we don't test it, we don't evaluate it. And then you see this beautiful paper Oh, I love it. Hey, if you're interested in this kind of video and you think, hey, yeah, this video really provided some new insight, this video really provided some value for me working here with AI system and working with reinforced models, and you say, hey, wow, this is amazing. Hey, why not subscribe? And I see you in my next model.